Hey, AP Chemsters, this is Mrs. Vanderwalle bringing you another edition of the Blank Walls. This is the beginning of Chapter 5. Chapter 5 deals with gases. This is the last of the unit that we talk about that's somewhat review for you from your first year chemistry class. So we're going to talk about pressure and volume and temperature and moles, and we're going to go into topics a little bit deeper than you hit in your first year chemistry class. Before we really begin, let's kind of lay out the groundwork again for how you successfully do a flipped classroom. Is when I tell you to pause, you need to pause and actually do your work. And check your work, check your units, factor label, write down all your units on factor labeling as always. That is really a good self-check method. Make sure that you're doing the problem right if the units end up right. So I'll be doing the same, and you should be doing the same. So if we need to pause right now and go get a calculator, that may be a good idea. You do need a calculator for probably every section in this entire chapter. So have your calculator handy, and let's begin. All right, so we're going to be talking about in section 5.1 about breathing. Hopefully everyone knows how to breathe. And, why do you breathe? What allows you to breathe? And it's all about pressure, that the air pressure outside is greater than the air pressure on the inside, causing, your lungs to fill up with gases. So breathing is putting pressure to work. So maybe a good idea at this point is to define pressure. What is pressure? Pressure in your physics class would be defined as force per unit area. And in physics terms, what is force? Force is your weight. It's mass times acceleration. You have area is typically defined as a square meter. So like how much weight do you distribute over a certain area? For gases, though, what is pressure? Pressure is the result of molecular collisions on surfaces. That's the idea of area again. So the presumption is that gases are always moving and colliding. So how can we make more collisions or less collisions on a certain area? That would be what your pressure is. So what does it depend on? The concentration. How many gas molecules do you have? Obviously, the more gas molecules, the more collisions you're going to have. Also, the volume of the container. If you have an itty-bitty container, then you're going to have more collisions. If you have a huge container, you're going to have fewer collisions. So we're going to talk a whole lot more about that when we talk about kinetic molecular theory further down in the chapter, but that's enough for right now. And so now we're going to head into section 5.2, which talks about these collisions. So first of all, we'll talk about some units of pressure and how did they come to be, all right? Well, if we have the picture of the Earth, here's my Earth picture right here. And then we have the idea that the Earth's atmosphere is roughly 30 kilometers high. So here's my 30 kilometers, if you want to jot that in here. And if you were to take a pole, a hollow pole, 30 kilometers high, that's actually pretty high up, okay? How much air will we trap? Well, the amount of air that you trap in that hollow tube there has pressure. Why? Because it has mass. It's going to collide. And so all those air molecules in that tube is going to cause pressure, and we define that as 1 atmosphere. Why? Because that's the pressure of 30 kilometers of gas molecules that you have trapped, okay? Now we have other units as well. Here is your kilopascals and your regular pascals. So these numbers are pretty important. We don't use them a lot. We use atmospheres probably the most, okay? Another one we have is 760 millimeters of mercury. How did we get that number? Well, that 30 kilometers of air has a mass and it has a really long tube. So what if we were to shrink down that tube to be 760 millimeters of mercury, so less than a meter? That mass of mercury will have the exact same mass as that 30 kilometers of air. Okay, so the problem here in the United States is we don't deal with the metric. So if you're watching the weather report and you listen to the weatherman like Steve Raleigh or somebody, they won't talk about millimeters of mercury, they'll talk about inches of mercury. Well, wouldn't you know that the height of 760 millimeters is exactly the same height as 92.92 inches? So again, that 92.92 inches of mercury has the exact same mass as 30 kilometers of air. So you scrunch down the volume, so your mass actually remains the same, but it's something that you can actually deal with. And then if you're interested, is 14.7 psi. What does that stand for? Pounds per square inch. You might hear of another unit called torrs, and the Italian physicist, I don't remember his name, it sounds like tortellini, but it's not quite that. Anyway, he came up with the same idea that 1 millimeter of mercury is 1 torr, and so they're interchangeable, okay? So that's what's going on right here if you look at this picture. So if you have atmospheric pressure pushing down on this tube of mercury, it's going to go up a height of 760 millimeters of mercury, okay? And that's where that number came from. So how are we going to use that? Well, let's check it out. Problem 1 is dealing with converting units of pressure. It's very, very important that you know how to do this, okay? Because like I said, atmospheres is probably the most common unit you're going to be working with, so it's going to be very important that you know how to convert things to atmospheres, okay? So it says the pressure of a gas is 49 torr. How many atoms is this? So you're going to factor label, aren't you? So how many atmospheres is 49 torr? Hey, what must go on the bottom? Hopefully torr. Now what's a torr? We'll scroll back up again, all right? So 1 torr is 1 millimeter of mercury, and 760 millimeters of mercury is 1 atmosphere. So I can substitute, the millimeters of mercury and torr, so I can have 760 torr is 1 atmosphere. And if you have your calculators, go ahead and divide. And your answer should be reported at 2 sig figs, and hopefully that is your answer. Okay, so the question is, well, how many pascals is this? All right, so how many pascals is 49 torr? Well, like I said, what unit must go on the bottom is torr, and torr is, you don't know a direct relationship perhaps with torr, but you do with atmospheres. But I'm not done yet because I don't want atmospheres. I want pascals, so I'll put atmospheres on the bottom and go scrolling back up. 1 atmosphere is, oh, here it is, 1.01 times 10 to the 5th Pascal, or 101,000 pascals. And here you go. So if you were to do your math, go ahead and do your math to 2 sig figs. What are you going to get to? All right, you get this. Now, I suppose you could make it a little bit shorter, that you could go directly from 760 torr to 101,000 pascals, and you'll get the exact same answer. I like to think of the atmosphere in this case kind of like the mole, where, if you can get to the atmosphere, you can get to anything else. So I just chose to do it the long way. So let's try letter C. The pressure of a gas is 980 kilopascals. How many millimeters of mercury is this? Why don't you pause this and see how you do? And this is how I did it. So I tried the shortcut. So instead of going directly to atmosphere like I did above, I showed you a little shortcut. So if this is equal to 1 atmosphere, well, 760 millimeters of mercury is equal to 1 atmosphere. And here I got this number, and I have 2 sig figs. So it's kind of like doing this. Do you remember I think it was the commutative property? So if A equals B and B equals C, then A equals C. Remember something like that? And so I'm using that idea to convert between, I guess, Pascal millimeters of mercury. So if 101.325 kilopascals equals 1 atmosphere, and 1 atmosphere equals 760 millimeters of mercury, therefore they're interchangeable. Okay, so let's go on to the next page and see how we do. All right, so we have the simple gas laws, Boyle, Charles, and Avogadro's. These are things that you should have seen from first year chemistry. But what is happening here with this section? You're looking at relationships. And here we want to talk about direct or indirect relationships. What does that mean? As one variable goes up, the other one goes up. As one goes up, the other one goes down. So if you have 2 thumbs up evidence, both of them are direct, then it'll look one way. If they are indirect, they're going to look the other way. So we'll be talking more about this, and honestly, that whole concept is really important for these sections. If you understand their relationships, then your life in this section will go a whole lot easier, okay? So the first one we're talking about is Boyle's law. Robert Boyle is considered the father of chemistry. He was the one to really take chemistry out of the dark ages. And back in the early time, alchemy was considered, mysterious, and you're trying to change things into gold. And everyone had their own recipes, so they had their own secret languages with their own symbols. And so Robert Boyle was the first one to actually make it so everyone can read about chemistry. He wrote the first chemistry book. So that's why he's considered the father of chemistry. And one thing that he got to play with were these gases. And he noticed a certain relationship, that if you have the volume of a confined gas is inversely proportional to the pressure of the exerted gas. And so look what happens here. If you want to make a straight line out of the relationship between pressure and volume, all right, here's your straight line. Look at this unit here. It's 1 over volume. So what if you don't want an inverse? What if you just want to see regular PV? Then look at this curved line here. All right. So what does this curved line tells you? That as pressure goes up, volume goes down, and vice versa. So what happens if volume goes up? Follow the line, pressure goes down. And something else that this graph is trying to show you, that if you pick 2 points on the graph, if you pick, 55 and 25 or something, all right, when you multiply those two together, you're going to get a certain constant. Well, if you pick 2 more points, maybe that is 25 and 50, you're going to get the same value, okay? And that's what that curved line does, is tell you that the pressure times the volume equals a constant, and this pressure times volume is equal to the same constant. I hope that this looks familiar, because we've already done the intro lab, and you should have had a sort of a curved line with your pressure and volume. So from this, we can say pressure 1 times volume 1 equals pressure 2 volume 2. It says it's the easiest form of Boyle's law to memorize. So here we go. It's an indirect relationship. So if it's direct, you're going to divide. If it's indirect, you'll multiply. All right. So that's why P1 V1 equals P2 V2. They're both equal to some constant, depending on which gas you're talking about. It depends on the temperature that you're walking about and how much you have too. But given the temperature is the same, the amount of gas you have is the same, the type of gas you have, then yes, those will be equal to some constant. So let's check out problem number 2. It says, consider a 1.5 liter sample of gaseous sulfur dioxide with a certain pressure of pascals. If the pressure is changed to a different pascal at a constant temperature, what will be the new volume of gas? Okay, so if I were you, I would be talking about, okay, what do I have here? I have a volume and I have a pressure. I am changing the pressure. I want to know what the new volume is. So what's the only things I'm talking about? Pressure and volume, nothing else. So that's my clue that I'm going to be using Boyle's law. So at this point, all you're doing is plugging in the values. So what's your pressure 1? I think it's a 5.6 times 10 to the third pascals. What's your volume 1? 1.53 liters. What's your new pressure? 1.5 times 10 to the fourth. What's your new volume? That's what you're looking for. So before I disclose anything else, well, first of all, here we go. Notice when I wrote everything down, I put my units in, people, put my units in. And what did pressure do? Pressure went from 10 to the third to 10 to the fourth. Pressure went up. So what would you expect your volume to do? You should expect your volume to go down. Well, let's check it out. Oops, I'm sorry. That shouldn't have appeared. I expect my volume to go down. So let's see what happens. So multiply these two numbers, then divide by 1.5 times 10 to the fourth, and I got 0.57 liters. I'm going to show you something. So if I cross out pascals, what's my only unit left is liters, and that makes sense because that unit is a volume unit. Okay. So yes, my units went, or my volume went down. I have 2 sig figs. I have my unit liters left. Everything seems to make sense. So let's look at problem number 3. Okay. Why don't you go ahead and try this one all by yourself. See how you do. Pause this. Okay, how do we do? Well, there's my formula. I am looking for my new volume again. But wait a minute. Do my units cancel out? Holy cow, I can't cancel out. This doesn't work, does it? So what should you do? You should convert. Now you can figure out the new volume. And there you go. So pressure went down, volume should go up, and yes, it does. So my atmospheres cancel out here. And so what's the only unit left is milliliters. So that's my unit. So look to have the part 2 section. Don't wait to be great.